See you later then.
So here's the list that you were sending.
You don't have to read all of it. Sometimes people don't even ask for it. But
I already read, and Svetlana would probably tell more stories if she wouldn't.
let's put this off to the side. So normally people speak for about 45 minutes, I guess.
If you go a little over limits, it's not a problem. When we have let's say satellite seminar series when graduate students present,
Okay.
and they typically present for like 50 minutes, and then committee tortures them for half an hour. This question. Where are you? Oh, please come in.
Yeah, I will.
All right. I have a question. Who is bringing the card here?
I don't know.
And who knows?
We need
Okay,
we need volunteers.
All right.
Is there something missing?
No, everything is good on your side.
Yeah.
We are looking for volunteers to bring supply of coffee and cookies.
Oh, yeah,
which is
yeah.
If he's so kind, we need to bring him to the dinner.
Okay.
Who's sitting here?
I believe Alexa.
We can decide it based on the content of the.
No, this is Alexis.
I don't know that person.
In the new faculty.
I'll sit here.
Good thing we didn't use half an hour for setting up.
Straight before you go into Denmark.
Still in Singapore?
Straight out.
Union.
Cooper Union.
In which state is it?
It's in New York City, in Manhattan, New York.
Okay.
Hey, I have a quick question.
Are you going to resend the invitation?
Oh, do you need to?
If you can.
Oh, I will try.
I'm getting like 200 emails per day. And
Yes, it's like. No worries. I can do that. And then the other thing, can we record this?
Yes. If Dr. Kulik approves, you'll do.
Yeah, it's fine.
Okay, I'll do that. Some people are missing it.
Oh, thank you. Okay, I think it is time to start. Welcome to the Biochemical Seminar Series. It's informal environment. Please feel free to refresh snacks. We invite Center invites both and relax. So today there will be a special speaker invited by special host Professor Susanna Chilina. So our speaker is Professor Heather Kulik from Department of Chemical Engineering at MIT. She got the BS from Cooper Union in 2004. Then got the her doctorate from MIT in 2009. And then she got 2 postdoctoral trainings at famous places, Stanford and Livermore. And then she returned back to MIT as a faculty, and since then she was very successful, achieving almost any possible award grants for young faculty. So, and also this fall I was witnessing her success as a special lecturer of the American Chemical Society at the ACS meeting, which is like once per year awarded to whoever made achievements through the year. So Professor Kulik is working in the area, and she will correct me if I'm wrong, that is complementary to traditional areas of science. So there is an informal splitting on experimental, theoretical, and computational. And she's doing the fourth way, the informatics and machine learning, that in some sense it is superior to all 3 of them and combines and gets laws of nature taking good parts of all 3. With this, please join me in welcoming Professor Kulik, and floor is yours.
Thanks, Dmitry, for the very good introduction, and to Dmitry and Svetlana for the invitation. unfortunately, if you've seen my ACS talk, then probably some of these slides will be a little familiar, but I see some new faces in the audience, so hopefully I'll tell you a couple of new things today. So what's true is I started my PhD actually at MIT was in material science, and then I had the chance to come back to chemical engineering, but I consider myself by training a computational chemist. So my first and really only love is thinking about what knowing about electrons teaches us about materials. And more recently, we've had some success in bringing machine learning into that. And so the way I like to frame this, because I really come at this from the perspective that atomistic simulation tells us a lot, is that we know that computational chemistry has been really helpful over the years in giving us insight where someone tells us what a structure is. So if someone tells us a class of materials or biological systems is important, then we know how to work about understanding that on a computer. And some of that is because it's increasingly routine to study larger and larger systems with approximate quantum mechanical methods. So if someone gave me the structure of hemoglobin, I could start to simulate large portions of this with what's called GPU-accelerated electronic structure, to start to study maybe even thousands of atoms here and look at why hemoglobin binds triplet O2 so well in different conditions and why that is we're breathing oxygen today. And in fact, going back to when I started my independent career, this is the kind of thing I thought I would be telling people about when I told people about my research and what I've gotten established on. But instead I'm going to tell you a little bit more about something closer to what goes on under the hood of hemoglobin, and that's this thing here. I've shown a simplified model of porphyrin, not quite the one in hemoglobin, but the porphyrin is a kind of structure that keeps recurring in natural systems, and it's something that nature came up with over many, many years as a useful cofactor for doing difficult chemistry. And now that I've just downsized the problem from thousands of atoms to just around 70 or 50 or so atoms, depending on functionalization, it's increasingly routine now, thanks to increasingly fast computers, to think about studying these porphyrins with methods even beyond mean field density functional theory, use so-called advanced correlated methods. And in particular, the metal here in the porphyrin is iron, typically, in natural systems. And this iron can take on multiple distinct quantum mechanical spin states, and so we need fairly advanced methods to be able to distinguish that. And so it's also increasingly routine if someone gives me the structure of a porphyrin or tells me what they want me to study, that I can start to understand what the structure-property relationship is. Where it's more challenging, you realize that in the area of computational chemistry, is to ask yourself, how would we use a computer to discover for a given application what the right structure we want is. So which atoms in the porphyrin matter? If we want to come up with our next porphyrin, how are we going to build it atom by atom? And so we can ask ourselves, is there a way to build a language, or at least that's what I did starting out in my independent career about 5 or 6 years ago. Is there a language that helps us describe this porphyrin in a smarter way that tells us why atoms matter and how to look for the next structure to build? And that's hopefully what I'll tell you about today. But what I just described is actually in large part old news. If you think about things, a number of people here are skilled in. This is old news if you go to specific areas of computational and chemistry and cheminformatics. In particular, for organic chemistry, closed shell organic chemistry, a lot of the things I just described, needing a language and so on, already exist. So for instance, if you spend any time with me today, you know, this molecule here, caffeine, is one of my favorite molecules. I've never turned down a coffee. And this is the SMILE string for caffeine. And so if we know the SMILE string, which is an invention of cheminformatics, we can rapidly produce this structure. And so we already have a machine-readable language that tells us something about chemical information. Force fields and semi-empirical theories routinely work in the context of closed shell organic chemistry. So we have fast ways to assess the properties of this caffeine molecule, even if we don't think knowing its structure tells us enough. And there are databases like Chembl or Zinc that contain millions upon millions of these SMILE strings compactly stored. And so as a result of that, we can rapidly think about going out and discovering where our next new porphyrin is in that space. So we can come up with a way to think about building new molecules. And if we don't want to sit there and study 7 million molecules all at once, we can exploit concepts from cheminformatics known as concepts of molecular similarity and dissimilarity to maybe just pick out the few thousand most interesting and compelling and distinct molecules from that subset. So all that already worked. So what I described that we needed already was fueling the rapid rise of cheminformatics and therapeutic drug discovery in organic chemistry. So all we thought we were going to do first, before we ever got to machine learning, was just try to translate this to open shell transition chemistry. But if you do, you run into a lot of roadblocks. So first of all, even if I wanted to build structures from SMILE strings in open shell transition chemistry, I would have to take into account challenges such as the oxidation state and spin state dependence of these structural properties. In practice, few force fields in semi-empirical theories actually work for open shell transition metal chemistry, particularly with multiple accessible oxidation states and spin states, so like I'll be talking about today. If we want to look into databases of transition metal chemistry, there are good databases. So we can look at the Cambridge Structural Database, but that consists of crystallized, so synthesized and crystallized experimental structures. And so this means that while they're interesting molecules, they're molecules that experimentalists have been able to make is stable enough that they can crystallize it and it's characterized it and they have published on it. And so at best what we can do is we can discover the porphyrin many thousands of times over. So if we look into the Cambridge Structural Database, we're going to find many, many porphyrins with different functional groups and so on. But it's not a place for us to truly discover. And then concepts of molecular similarity and dissimilarity, if we just blindly take the ones that work for organic chemistry and apply them to inorganic complexes, we're not able to discern the metal and oxidation state and spin state dependent concepts of similarity that are actually so essential to distinguishing why certain transition metal complexes behave like each other and why others behave dissimilarly. So what we ultimately did first was we took a divide and conquer approach, motivated by a very simple observation. And I'd say this underlies, in general, our approach to machine learning and discovery in transitional chemistry. And that's if you look at a series of organic molecules and you just lay out what the bond length is, it follows a very intuitive scale that you likely learned in Gen Chem, which is that if we know the bond order, say moving here from a triple bond to a double bond to an aromatic to a single bond, they follow a pretty linear trend that we can see by eye, just going from 3 to 2 to around 1.5 to 1. And this is something that a force field can capture well. So the blue dots overlaid here on this line are what a force field, just an off-the-shelf force field, is able to predict. If you tell it you have a triple bond, double bond, aromatic, and single bond, it gets pretty close to this trend that's fairly linear. If we go and we look into an inorganic complex, this happens to be iron 2 or iron 3 hexacarbonyl. And all I'm doing here is the same exact chem-draw, the same exact structure. It's always iron hexacarbonyl. And all I do is I change the spin and oxidation state. You can see I have a highly nonlinear trend. So iron 3 has less spin state dependent metal ligand bond length. That's what I'm plotting here on the same scale, but shifted. Whereas iron 2 has more spin state dependence in the metal ligand bond. So the first time we then took this divide and conquer approach, what we did was we took the force field and trusted it in the cheminformatics tools wherever we could trust them, and we applied a series of heuristic rules and information from DFT that we stored in a database to then help us decide how we were going to assemble transition metal complexes and set things like the metal ligand bond length. Because this red dot here is the only thing that a general purpose force field would be able to predict about this molecule. So if you get one of these right, it's not actually even parametrized or trained on this particular model, but this is what it came up with. So we did this, and this software that underlies everything I'll tell you about today enabled automated command line structure generation, input file generation, so we could then pass all of these structures and input files for the automated high throughput screening and transition metal chemistry. That was the very first start to getting to the question of how do you find the next porphyrin is how do you accelerate and automate the process of screening transition metal complexes. And so we did the divide and conquer approach throughout everything we did. So for instance, I told you there are multi-million molecule libraries of organic molecules. So we just used them, for example, for ligands and carried out the same type of filtering and searching and similarity and so on. And everything I'm going to describe today is in an open source code we call MolSimplify. It's on Conda and GitHub and on our website. And it underlies everything, all the scientific advances I'll tell you about. But this is really where it started, and I'm not going to mention more about its features beyond that, except that every model and every approach I show you is something that's enabled by this code. And so the first thing we went out and did once we had this code was we carried out high throughput inorganic chemistry, something that was being increasingly done in the solid state material science community, as well as being done in organic chemistry, but we extended it to more challenging spaces where it hadn't been done before. Both in the space of thinking about functional materials, including designing precursors for quantum dot synthesis, polymers for separation, but I'm only going to tell you about one small example in catalysis today, except to note that I'm going to show you the slide again after we've done it with machine learning, and the scale of these types of applications is typically, at this point with high throughput screening, just on the order of around 500 catalysts and materials. And so the first example we focused on is a challenging reaction, and we picked just one part of it, but just as a refresher for those of you not familiar with it, most of methane that we have in high abundance gets flared each year because it's difficult to transport methane gas. If we were able to convert it to methanol directly, we'd store a lot of the inherent energy in methane and have a transportable liquid fuel. And so methane to methanol has been a holy grail reaction for a lot of chemical engineers for some time, and it happens to be a type of thing that natural enzymes and biomimetics are able to do in small measure, typically at something like an iron site. And so I'm showing this process here with N2O, an industrial oxidant that's easier to work with, but when nature does this, it's with oxygen from the air. So we can think of the first thing that typically has to happen to enable direct methane to methanol conversion is the formation of a high valent metal oxo intermediate that then abstracts a hydrogen from methane, which then in turn rebounds. Methanol releases, and the cycle starts over. There's lots more complications to this, but I'm just going to focus on these two steps today, the formation of the metal oxo intermediate and the step of hydrogen atom transfer. And what a chemical engineer would normally think about in modeling these things, so a person working in computational catalysis, particularly in heterogeneous catalysis, is they would invoke a scaling relation. What they would tell you is that if you make the oxo too stable, so the oxo forms really favorably, it's going to be unreactive towards hydrogen atom transfer. And normally in heterogeneous catalysis, you would build up lots of these scaling relations, put them all together, put it into a kinetic model, and you end up with something that's called a volcano plot. And what the volcano plot tells us is because all of the steps of our reaction are coupled, there's only one set of catalysts sitting at the top. There's only really one way for us to win at this reaction. And so this is advantageous from a computational chemist perspective because what this typically means is that we can screen quickly one descriptor. So in an informatics style approach, we screen one binding energy and it tells us how all these other binding energies are related. But the limitation of this is that the most precious metal on the planet, the most difficult to synthesize material, could be the only thing sitting at the top of this volcano. Or even worse, the top of this volcano we predict that we can never get might still be too short to make it worthwhile to carry out this process. So we were just interested in answering with MolSimplify if scaling relations still held once we moved to molecular catalysis. And this was actually something people hadn't really looked at before we got into it. But we, to take a look at this, what we did was we built small models of catalysts, and we built specifically automatically 540 catalysts generated with MolSimplify, and sort of how automatic this was the student involved set up these calculations, left town for an internship for 4 months, and then we looked together at what he had when he came back, because the calculations just all ran in the background, which of course is living the dream, because you can imagine replacing that with vacation or whatever else. But in any case, what we did to try to perturb the local metal environment, and this is all iron 2 high spin, which was a limitation of this initial study, was we looked at stretching and compressing the metal ligand bond. We looked at distorting the metal in and out of the plane. We changed how the metal was coordinated: nitrogen, oxygen, phosphorus, sulfur. We also changed termination to look at local termination effects. And this is what we saw. And so I don't know about you, but I don't feel comfortable drawing a single straight line through this data. So what this tells us is that the picture of the single line I drew for you between the thermodynamics of the oxo formation step and the hydrogen atom transfer step, it doesn't hold as tightly as this picture in heterogeneous catalysis tells us it would. But there's some structure here, so if we are losing at oxo, we seem to win at had, and vice versa. So we wanted to look a little more closely at what was going on. And so here is coloring it by coordinating atom. You can see that there's some effects that have since been shown on related materials, which is if we strengthen the ligand field, we go this way. So strengthening the ligand field makes oxo formation more favorable while worsening hat. But we could focus on just one subset of this data. And specifically what we see is that actually if we look at just the oxygen coordinating catalyst, there is some structure there. So it looks like we have 3 lines, right? So if we look at what forms one single line, this is metal ligand bond length stretching and compressing. So if you asked me beforehand which would have been the most important thing, I would have thought, oh, that's probably going to play an important role. That's what a catalyst scaffold is doing. But in fact, the metal ligand bond length is just tuning the ligand field effect. The way that we are stretching and compressing, we're just tuning the ligand field. And it's actually the metal ligand plane dihedral that's causing us to break apart into these 3 lines. And so if we go back and we color all the data, we see this trend generally holds. That if we can distort the metal out of the plane, we can win at hydrogen atom transfer without losing at oxo formation. We can shift off the line that we'd be on otherwise. And even within each of these lines, there's still significantly more scatter than people would normally be comfortable with. You can easily read off one way and end up with a 5 to 10 kilocal per mole error on the other step if you assume that you're sitting on the line. So this suggests there's more flexibility in single-site catalysts that would give more access to opportunities for design. And so I'll skip past this since I'm not in a room of chemical engineers necessarily, except to say there are scaling relations between thermodynamic intermediates, that's what I've just showed you, and it's called a BEP relation when it's between kinetics and thermo, and specifically specific types of reaction steps. Here the oxo formation step, and here the hydrogen atom transfer step. In one case, it's also possible to break the relationship between the transition state and the intermediate, whereas in other steps it's not. And this is advantageous to know which case you're in, because if you have a scaling relation like this that holds, then you don't have to waste all your time computing transition states. But this was just data. So we used data to find something that we didn't know before. But ultimately, our goal is to get new physical insights. And so the question might be, why was this the way it was? Why was it so easy for us to break scaling relations? What are we doing? And it turned out if you took a look at the energy levels of the D states, this is often usually referred to as D-band center and D-band width in bulk materials, but here I'm just showing discrete states because we have a single metal site. What ligand field really does is it just shifts all of the D states around rigidly. Whereas when we're doing this distortion out of the plane, we're actually shifting levels with respect to each other. And the result is that we're able to move around differently different states that participate in different reaction steps and different barriers. And so this is why distortion is a good path to thinking about designing these catalysts. It turns out that experimentalists have known this, and for some time, you can look into the Cambridge Structural Database, and you can see a fair amount of distortion on known materials that could be good catalyst mimics, or at least biomimetics. And you can also think about doing this in materials by engineering in this distortion through post-synthetic modification, exchanging one metal for another. But all I've told you so far is about exploring chemical space neighborhoods. You can think about what would you need to actually get to answering the question about what the next porphyrin is, and you realize quickly, if you do the math, that all the things you need to understand about a transition metal complex, all the things you need to be able to design are so high dimensional that we need something better than just being able to do 500 DFT calculations on 500 catalysts with different intermediates in a few months. So the design space we have access to with transition metal complexes is vast, and it's vast because we have to worry about things like which possible spin state are we in? Are we in a high spin or low spin state with the metal center? There are many different metals we're often thinking about. Most of my talk today will be about chromium through nickel. My group has moved into other states and other metals since. In particular, iron here, if we just pick out one that I've already talked about, iron is well known to have a large number of oxidation states, which in turn have a large number of electron configurations. And then we can think a lot about relatively large ligands, ligands of different orientations, and so on. And so what we can reach the conclusion of is that we're only ever going to get so far by doing 500 high throughput DFT calculations. We need something faster than DFT. So that's where we were in, I guess, around 2016 when we made the jump into building machine learning models. And the way this came about was my student, John Paul Genet, and I were talking, and he was a first year at the time, and he needed to do a homework assignment for his machine learning class. And he asked me, what would you like to be able to predict? What would you like me to build my project on? Which I'm very grateful for. Many of my students who've taken machine learning classes since don't tell me what their homework assignments are. But and I think I thought my place was pretty secure as a modeler and as a person who had spent my career around 10 years at that point building chemical intuition. And so I gave him a very strong, long list of things that I thought he'd never have any chance of predicting. And the first was I wanted him to be able to predict the quantum mechanical ground state spin of a transition metal complex, as well as the splitting between the ground state and the next accessible spin state. And because I knew we were going to use as training data results from DFT and I didn't trust them, I wanted him to be able to predict the sensitivity of that prediction to the exchange correlation functional chosen. And one of the motivations for being able to do this, as I mentioned, is that there were no phenomenological models. So if we wanted to be able to predict the ground state spin of these types of molecules, all we had access to was DFT, and the types of calculations we would need to do in order to just get at least an estimate, which we may not trust, would be days. And then, ultimately that list grew over time to other things. I'd just like to point out specifically, because we had this toolkit that was automating the assembly of transition metal complexes, we specifically didn't want to use geometric information to make any predictions, and we wanted to be able to actually predict the metal ligand bond length. And I'll tell you about some other applications too. The thing to note is that we restricted ourselves to mononuclear octahedral transition metal complexes or cases where any of these sites are empty. The rationale for this was that it was at the bleeding edge of where DFT could be trusted. We used common ligands to build our data sets, which were typically on the order of a couple thousand molecules, usually 5 metal +2 and +3 oxidation states and at least 2 spin states. And we addressed the exchange correlation sensitivity challenge by varying the amount of Hartree-Fock exchange in the functional because it has the strongest effect on predictive properties of transition metal complexes. So anytime you build a machine learning model, there's always some trade-off. But it's pretty similar to the trade-off that you would think about when you think about building any relationship in your mind as a scientist or engineer. So we typically think about if someone gives me a set of 6 molecules that all behave in a certain way, can I map that in some way or explain from the structure of those molecules why they behave the way they do? And so we are, as scientists, always building structure-property relationships all the time. Machine learning can be thought of as a slightly trendy way of saying that on much larger data sets. And so the key thing to note is that there's always some trade-off. So if you have a ton of data, you might use a complex model. You might not care about your representation. But we were specifically interested in accelerating discovery in transition metal chemistry. And so one of the things we thought a lot about, and I'm going to show you today, is this question of how do we choose how to tell the model what type of chemistry to care about. And so what was conventional at the time was to think about what we can to a quantum code, which is what are all the atoms' positions and what are their identities. But we also knew that there were theories like ligand field theory that work really well that throw away almost all the information of a transition metal complex and focus only on the metal and its nearest neighbor. So we had this idea that probably the right answer sits somewhere between these two. And then another thing to note is that the smallest transition metal complex we could ever even trivially think about studying is quite large. So the calculation and data set sizes that we want to obtain are limited in comparison to other data sets. And then I'm going to show you a range of models today, primarily kernel-ridge regression models and neural networks. But we wanted to balance both being able to interpret and learn from our models, as well as to be able to carry out and ultimately accelerate that discovery. So we actually did representation development in 2 ways. And I'm going to show you them side by side because both work. So in one, we carried out an ad hoc representation development. And what this involved was going back to that homework assignment I mentioned. the student and I sat down together, and I would say, well, I know the metal matters, I know the coordinating atom matters, and these are some other things we figured out recently, like differences in electronegativity around the metal matter a lot. And I would just throw at him things that I thought should matter. This is an ad hoc descriptor set. We also extended it to add other things, such as from the cheminformatics literature, the truncated Kehr shape index that told us something about the rigidity of the molecules. And all of this was very heavily engineered towards metal local features that we knew mattered the most for transition metal chemistry from other high throughput screening. And the first time we did this, we retrospectively called it MCDL25. But there are other properties people were really focused on that depended a lot on the size of the molecule, and we threw away basically all information about how big the molecule is and so on, and this isn't very satisfying. So every time we want to solve a problem, you need someone like me to sit down and come up with a series of descriptors. So we also built a systematic way to develop these representations by extending something called autocorrelation functions from the early 1980s. We revised them for transition metal chemistry. And what these are products and differences of heuristic properties on the molecular graph. So they're still geometry free. What depth here means, or distance here means, is how many bonds away something is on the molecular graph. And we extended them by both defining a product and difference autocorrelation, as well as adjusting the scope to include ligand-centered and metal-centered. And so how this works is, and so these are the 5 initial properties that we used. Nuclear charge, electronegativity, covalent radius, topology, and identity, and these are all associated with each individual atom in the molecule. They don't require any prior calculation, so they're really fast to featureize. And so all of these can be built as analogous to MCDL25. So for instance, the number of atoms in a system is the zero-depth identity rack. These over here, the metal and coordinating atom, are the zero-depth ligand-centered or metal-centered Z-rack. This one over here is the one-depth ligand-centered pi rack, and so on. And I'm going to break down property predictions in terms of the substituent racks that matter most later. And when I do, I'm going to color nuclear charge and electronegativity as more electronic in nature, whereas these covalent radius, topology, and identity I will color more as geometric in nature. And then the other thing is that some of these racks are very metal-centered, and so they only encode information about what's going on with the metal, so I will call those proximal in nature, whereas the ones that cover everything, so these sums can expand to covering the whole molecule, I will call those distal in nature. And so in practice, these expansions to a depth cutoff of 3 leads to around 150 possible features for this and 25 for this. And so this right here is a principal component analysis that shows why it's worthwhile to do this representation development. Here is a whole molecule descriptor that was sort of standard at the time that people would use. And this principal component analysis shows that the whole molecule descriptor has done a really good job of clustering our different complexes by size. So this one here is 150 atoms, this one here is 37, and we color by size. We see we've done a really good job in the first 2 principal components of separating the systems by size. But if we look at a property we want to predict, which is the spin splitting between the high spin and low spin states, these molecules, because their coordinating environments are almost the same, they have actually almost the same property. And so by putting them really far apart from each other in the feature space, it makes the model have to work much harder to predict that property. If we look at our local representation, you can see the local representation puts those 2 dots much closer to each other, and so the model has to work much less hard to learn that these 2 molecules behave more similarly. So if we had infinite data and we had nothing to worry about, then we wouldn't care. But what this does in practice is it makes it much easier for a model to exhibit good performance. And so as a result, using MCDL25, we were able to predict 97% of DFT spin states. So what we're calling the ground truth here is DFT data. And so what our goal here is to predict in a second what we normally would have spent hours or days predicting. And so you can see we're able to do that. It turns out with this functional, we do a pretty good job of predicting trends that would be observable from experiment, but I'm not going to talk about comparison to experiment. We're not going to have time today to talk about it. The other thing to note is that these black error bars are credible intervals from something called Monte Carlo dropout. We were always interested in knowing, even if the model makes a prediction, how certain is it of that prediction? And hopefully I'll have a moment to tell you about that as well. But as a result, we were able, on the same data set size, to go from a representation that wasn't suited for inorganic chemistry to one that was, and cut the error in the prediction by tenfold over the same data set size. So this is MCDL25 again, which is what I just showed you, but these are our rack feature sets. This is before feature selection. This is after down selecting to a feature selection subset that's actually close in dimensionality to MCDL25. And this is what we call the universal set because it's been selected for balanced performance on multiple properties. And so what to note here, it's not super important to me at this point, but it was novel at the time, is we were able to predict the DFT result that would have taken us hours or days to an average error of around 2.5 kilocal per mole with the MCDL25 set that came from my intuition. And we were able to get to sub-kilocal per mole with these rack feature sets, even after feature selection, so it wasn't just that we were overfitting the data with higher dimensionality. We were able to extend this to other properties, like predicting the solvent and thermal-corrected redox potential or adiabatic ionization potential. And we could also do things like replace the force field I told you couldn't predict the metal-ligand bond length. Here is our neural network predicting the metal-ligand bond length, and you can see that it can predict it to, on average, around 0.01 angstroms, whereas this is what we would get out of the universal force field. And the result is now, when we do that molecule assembly I told you about in MolSimplify, we use the neural network to set the metal-ligand bond length and the organic force field to do everything else. But an interesting question might be, MCDL25 came from my intuition over about 10 years of research, whereas this rack approach was a more systematic approach, and the rack approach beats what my intuition said. So is there any relationship between them? So this is encoding by proximal in pink, middle in green, and distal in blue, the MCDL25 feature set. This is what rack 155 looks like. And this is after feature selection. So this is compare the rightmost one and leftmost one. By definition, the expansion gave us a lot of blue, but you can see it's after feature selection, MCDL25 and URAC26 agree quite well. The main distinction here is that what we got wrong with our intuition and our ad hoc approach is that we underplay the amount of mid-range information that was needed and overestimated how much proximal, but both generally agree that the amount of very distant information from the metal should be a relatively small portion. But then we're interested in being able to use these models for discovery. So it's not enough to just report test errors. We're interested in looking out of distribution at totally new chemistry. And you can see we did pretty terribly. So if we did well, all of these points should lie on the line that the calculated and predicted spin splitting should match. But I've color-coded these by errors in kilocal per mole. And I would say the blue and green points are acceptable, whereas the orange and red are way too high. And so we're interested in going back to those Monte Carlo dropout credible intervals to see if they could tell us why we were performing badly in some cases, and we found instead that they were overconfident. But if we looked at the data by eye, we could see the difference between the points that we were good at predicting and the points we were bad at predicting, where the ones we were good at predicting actually looked a lot like our training data, and the ones we were bad at predicting looked nothing like it. So we defined in MCDL25 the Euclidean distance in feature space, so how distant in feature space were the molecules, as a heuristic cutoff for when we should be able to predict with a model. And we set a value of 1 in these normalized units, and the result was that if we did that, we could throw away 11 of the 12 points that we performed poorly on, and keep most of the points that we performed okay on. And the result was just using this cutoff, we could cut the error from unacceptable to something not too far above what our original test error was. So this gave us a path to thinking about using the neural net to score and predict leads in discovery without going too far away from what it knows. But another thing that we wanted to be able to do was actually extract physical meaning and some interpretation from the models. And so we carried out feature selection and looked at, as I've already shown you, some of the feature selection results, which features were most important. So here are the porphyrins of abstraction of around a couple thousand data points. And I'm going to use that coloring I told you about earlier. I'm going to color the atoms as blue if they're more electronic racks that matter for the property prediction, or yellow if more geometric. I'm going to make the atom big if it matters a lot for a prediction, small if it doesn't matter at all. And so using two different cutoffs for a 41 or 26 feature spin splitting set, which is this one here is URAC26, which I already showed you, what we can conclude is that ligand field theory works. So the electronic properties around the metal are the most important for predicting the spin of a molecule. is what this is telling us. And atoms far away from the metal matter a lot less. But if we look at another property like bond length, a different picture emerges. So we see now that the property prediction is much more balanced and all over. So yes, the metal and the ligand matter a lot. The direct connecting atom matter a lot for defining this bond. But depending on what's near that nearest neighbor also matters, and it's a combination of geometric effects, such as are there bulky groups, as well as electronic effects, such as what is participating in that bond. And then where things get really interesting is that redox potential lights up an entirely different part of the molecule. As you can start to think about orthogonal design, how you would tune the spin state by tuning atoms close to the metal, and redox by tuning atoms far away. And so this gives us not just property prediction now at faster and faster speeds, but a roadmap for different types of multi-objective design. And this is what this looks like in pie chart form. And so now that you have these pie charts, you can extend them to other things like catalysis and look at how the map of these different types of features informs different things, such as intermediate formation and catalysis here in that same reaction I told you about a few minutes ago. So I'm running a little slow, so I will skip through this, except to say our model predicts properties dependent on Hartree-Fock exchange. And so one of the things we can address is the fact that when we're learning what is a good molecule and what is a bad molecule, we're doing that dependent upon the method that we use. And the biggest worry we can have in these types of approaches is that something that we call good or bad switches, depending on the level of theory we employ. We overcome this in the first shot, or we did a few years back, by training on a series of functionals. So what we can do is we can look at regions of space where the lead is no longer a lead when we change the method, whereas other regions where the leads are all roughly in agreement. And we're now looking at spaces where the method sensitivity is high versus low as a way to overcome that in screening. Second challenge of thinking about uncertainty and letting a machine learning model pick for us what a good molecule is the model's confidence itself. So I already told you about how we used feature space to identify when the model should be really uncertain, but that works best when the feature set is already really heavily engineered. We ended up moving to something known as the latent space distance. And what that is that when you realize what a neural network is doing, is it's passing the features through a series of layers that are then amplifying to better fit the data what is actually important and what is not. So what we do when we use the latent space distance is we look in the last layer of the model before which a linear regression occurs, and we look at where the model has moved the data to, and we now look at a new point as where it sits in that latent space. And the result is that we have really good error control. So we can set our budget of how conservative we are, and the result is of the data we're willing to predict on that we don't know anything about, we can monotonically drive down the error. So here is a scaled latent distance, and as we move this way, we're getting more and more conservative, and the result is that we can go from having 7 kcal per mole error on a big set of data to only a couple kilocals per mole on the data we are most confident in. You can do the opposite. You can say, well, these are all the points I'm unconfident in. Let me go out and do the calculation or the experiment, ingest them, and then retrain the model. When you do that, that's called active learning. And so when you employ that on these same types of data sets, removing the 10 points that are the least confident based on latent space and then retraining outperforms all prior ways people normally use to carry out active learning. So this is just to say that there are 2 different ways to think about when the model actually knows what is the right answer when it looks at a new chemistry. And we apply this generally in combination with evolutionary algorithm optimization. Evolutionary algorithms themselves are nothing new, and we did nothing really special with them. But we're interested in carrying out exploration of a pretty large design space. The first time we did this was a project with a high school student, Lydia Chan. She was a rising senior, and so we wanted to do something that was in the scope of what she could do for a summer. And so we took a look at around 5,000, really a toy problem, 5,000 transition metal complexes with the goal of finding spin crossover complexes, because we had neural networks that could predict spin state ordering, and spin crossover complexes have near degenerate spin states which can then change in response to stimuli such as light, and the spin state switches in response to light or temperature, and as a result you can think of them as useful molecules for sensors and switches. And because we were using a genetic algorithm, we're going to code this design space in terms of genes for the metals and the ligands. And a schematic of how this typically works is we start with some initial pool. We evaluate the fitness of these. The fittest survive. We also have mutations of the genes and so on. And then we ultimately end up collapsed into some best result. And because this is a fairly local optimization scheme, we run this several times. What's special about this is how we're going to go ahead and define fitness in the context of the neural net. So with a neural net, we can obtain which of these are fit and which aren't in less than a second. If we tried to do it with DFT, it would take us hours to a day because we need to do at least 2 geometry optimizations for each one, and if we get stuck on one slow one, it would take us a really long time. But we don't know if we trust the neural network when it makes this prediction. So we have to be aware of model uncertainty. So we want to go to the places the neural network knows the answer, and also thinks is a fit compound. And so the first way we did this, we've since done this a couple other ways, is we have a property term in our fitness function. So if the spin states are near degenerate, then it's a high fitness compound because this approach is 1. But then we also have a product with another exponential, which is the degree of uncertainty. And so it's a distance either in the feature space or the latent space of how far the new molecule we're testing is from available training data, so we know when the model is confident. And so the goal here is so that we carry out this optimization and we end up in a space that's both promising and that the model knows something about. And so this worked, and we did it. And this is just sort of a cartoon to say we could come up with hundreds of leads in seconds. This is the convex hull here, and so you can see most of the data is converging to sitting inside that convex hull of where the original training data was, or not going too far away. Here's more of a 1D plot of what happens. If we let things go, the neural network would optimize to new complexes that I was very excited about but knew nothing about, whereas when we control uncertainty, we're balancing both going to new compounds and going to compounds that aren't too far from training data, and so we end up with this type of plot. But you might be asking, well, did we do well at all? Did we predict anything? Or did the neural network just predict garbage? And this is how we did. We did okay. Because of the way we defined the challenge was we needed the spin states to be within plus or minus 5 kilocalories per mole of each other, and we started them at a very large range of initially plus or minus 5 kilocalories per mole. Around 2/3 were confirmed using DFT as the ground truth and spin crossover. And so this is dramatically enriched from the original design space, and the full DFT on this design space would have taken many months to years. And so there wasn't a perfectly monotonic result. So for instance, a relatively far compound in our distance metric had a relatively small error, whereas you might notice that all of these dots sitting up here were green. And most of them are mid-range heteroleptic manganese complexes that were different from any available data in our training set in terms of being homoleptic. So it was something that the model shouldn't have rightly predicted but didn't look so far away. And ultimately, if you collapse down all of the data and look at what was going on here, the 40% of the data was within the original baseline error, test error of the original trained model. This is MCDL25, and 80% was within twice that baseline error. On average, our error was around 4.5 kilocalories per mole. So we were able, on average, to control our error to be only a little bit worse than our test set error and go out and enrich and find new leads for DFT calculations. We've since gone on and done this in a number of other systems. An example here is we asked the neural net to find us molecules with 4 EV band gaps on average from a 14,000 complex space. And the average over 10 leads selected by the ANN-driven GA when evaluated with DFT was 3.97 EV. So you can see that you can do even better with better trained models. We also applied this to discovering catalysts in large spaces. And so the result was that doing this took us from where we were at the start of this with 500 catalysts or a couple hundred leads, and now you can see we're easily in the thousands of catalyst spaces. In fact, the most recent paper draft on my desk is more like a couple million, but I don't have enough time to tell you about that today. Except to say that this is now a way for us to, with quantified uncertainty, explore larger and larger spaces. So you might be wondering what's next. aside from just publishing larger and larger spaces, there are other challenges to think about, and that's how we're actually carrying out computational chemistry. And I'd like to just finish my talk by telling you a little bit about that. So if I think back to how I carried out my PhD research, and how some students in my group still carry it out, is I try to think about how much of what I do is really that complicated, and how should I be spending my time. So normally what I would do is I would choose, and back then in my PhD, build by hand a molecule to study. Then I would come up with a way to decide which calculation method, which code, and which parameters I should carry out. And then I would go and maybe check some papers or ask an advisor or a student in my group how I should really carry out this calculation. Then I would run and check on the calculation, and then I'd probably go back and read some papers again, see if my calculation made any sense. I would analyze it, come up with some analysis tools, and then I would repeat this over and over again. And at the end of running through this workflow several times, the output for me was a PhD thesis. But how well that knowledge transferred to anyone else was fairly limited, except for what people could read from my paper. And so I started to think about how much of this, how complicated my high-level functioning was, and how much of it could we actually build into an autonomous computational workflow. So you would think we would need the automated selection and building of molecules. We need something that autonomously decides for us what the right method is. We already have data-driven models. We want something that automatically runs and checks on calculations for us and carries out automated data analysis and repeats. So I broadly say that I've already told you about how we've done these three things. And this one's in progress. I'm not going to tell you about that today, but I'm just going to finish with an example of how we've built models now that can decide which calculations to carry and monitor them. And so to do so, we have to define what we call success and failure. And it turns out we have lots of failures in open shell transition metal chemistry that I haven't told you about so far. So if we're letting a machine learning model decide for us what a good molecule is, we need to know if that molecule can feasibly have a DFT calculation carried out, at the very least. We need many more things, but that's a preliminary issue. And one example could be that we set up a calculation, we set up a molecule, and it isn't actually even stable in the gas phase, and so it falls apart. Or our picture of a single particle cone sham DFT really fails, and where we expect the metal to have most of the spin, it ends up everywhere else, and this is at least a preliminary red flag that a single reference picture is going to fail. Or that this is something that needs to be looked at by eye and cannot be used in automated computational chemistry. So what we did was we took the racks I told you about that worked for property prediction, and we trained classifier models on a series of good and bad calculations. What we wanted to do was predict, would a calculation succeed or fail? And the result was we could do this to about 88 to 95% accuracy. We could predict before ever running a calculation if the calculation would succeed or fail if we knew the chemical composition. And the result would be that we could run about half the calculations we normally run in about a third of the time to cover most of the feasible space, because bad calculations take a lot longer to fail than good calculations take to succeed. And this is just a confusion matrix of these two predictions combined. But the question to ask, I think, is this actually transferable to new chemistry? And the result is no. So we need to know what good and bad look like, and it's really hard to transfer good and bad to new oxidation states, new metals, and so on. And so when we went to a diverse test set, our accuracy dropped so much that we wouldn't trust this model to make decisions for us to what to calculate or not calculate, because it's not that much better than random guess. So here what we did was we built another model for UQ, trying to identify where the classifier knows really well if the answer should be yes or no. And the result was that we could predict on a smaller subset of the data back to the accuracy that we were able to achieve on the original data set. So we could at least predict on a third of the data without ever running the calculation whether or not we should run it. But we wanted to do better than that. So we took in mind that when you're running a calculation, there's a lot of information being generated. And that's things like properties about bond orders, Mulliken charges, what is the nature of the gradient, and what is the geometry as it's evolving. And so using these features, we trained a convolutional neural network on all of these features and used the data that gets generated during a geometry optimization. So at each step, we obtain this information. And this model generalized much better to diverse data. When pairing it with uncertainty quantification, which is what the green, blue, and gray dots are, we can see the model gets more and more confident the more information it has from the geometry optimization, and that using it paired with this is telling you which things are falling inside the land space entropy cutoff, and this is our prediction accuracy. We're able to keep prediction accuracy at close to 95 to 100%. If we don't use the uncertainty quantification, this performance is still much better at every time step than we had when we had the original composition only. So the question might be, what is this information telling us that's more generalizable and that is more informative than composition alone? And to do so, we looked at an analysis technique that's useful for convolutional neural networks, gradient-weighted class activation map, that helps us distinguish why convolutional neural networks predict what they do. And in particular, this is the features of a hummingbird that are useful for predicting why a model can detect that this is a hummingbird, let's say. And so on our data, this is what this looks like. These are our features scaled blue and red and moving around. And these are 4 different cases I'm going through. And then this is the gradient-weighted class activation map. When the gradient-weighted class activation map thinks that a feature is important, it lights up green. So for instance here, this thinks everything is important, whereas this one thinks only the beginning parts are important. And so the result is that what I'm showing you is this example is a calculation that converges well and quickly. And so everything's very smooth, and so the model uses all that information to make its prediction. And this is a case where the optimization went bad quickly, and the model focuses to the early events where that first occurred. But there are other cases where something can have some wiggles in the beginning and still turn out okay. It can have some wiggles in the beginning and only turn out bad at the very end. And so this is a path-dependent property. So just knowing the composition is never going to be enough to get us to 100% of predicting will a calculation succeed or fail. But using this online information that we can usually get within the first couple hours of an optimization can tell us, even in totally diverse sets, whether or not a calculation should be wrong. And so this is at the very least a first step towards taking some of the tedious steps out of the hands of computational chemists so we can get further towards thinking about designing materials and less about whether or not our calculations are running and whether or not we need to check on them and so on. So I've told you about a lot of things and I've run a little bit long. I apologize for that, but I promise you this is my conclusion slide. So where we started in all of this was bringing tools that existed in other fields to high throughput inorganic chemistry. And once we had tools that allowed us to do high throughput screening and open shell transition map chemistry, it was very natural for us to start building machine learning models for property prediction that we then fed back into the software. This ultimately allowed us to accelerate the discovery of new materials. And some of the outstanding challenges we're thinking a lot about today are how do we take ourselves out of some of the tedious parts of this loop by enabling fully autonomous computational chemistry. All of the models I've told you about today are in MullSimplify. This includes our prediction of if a calculation will succeed or fail. It includes the generic algorithm and includes all the neural networks if you'd like to play with them. I'd like to conclude by acknowledging the students who did the work. MullSimplify was built from the ground up with my student Timothy Nevis, who's one of my first PhD students. The machine learning work was pioneered by Jean-Paul Genet, and then I've had the chance to tell you about some work by Chen-Yu Wang and Chin Andy today, as well as broadly this part of my group that works on these types of systems. And thank you for your patience and attention.
So, thank you very much. This presentation is open for discussion and questions.
So, thank you very much for your presentation. That was excellent. So, sorry, I'm not a chemist. I'm coming from the engineering department, and maybe some questions were so simple. So, you show a molecule, and from the geometric side, you said that one of the structure was good and one of the bad. So, you use machine learning to generate a best or most optimized molecule for your target value or no? The question is that molecule is completely new or no? You try to optimize the current material or current molecule
Yeah, I got it. So there are a few things we did. In the first part of the talk, what we did was we selected a molecule we'd like to exist, and we used the neural net to build a structure close to what the optimal should be. In the middle part of the talk, we picked from a big bag and pool of possible molecules we've never seen before that we assembled by some genetic algorithm, new molecules. And then the third part of the talk, what we said was, if those new molecules were predicted by the neural net to be good, we still needed some validation of their stability. If we were experimentalists, we'd say that they could be synthesized or they were stable at room temperature. We haven't pushed that far yet. All we said was that if we started that structure and carried out a geometry optimization, could we still see something that looked like that structure? And so what we called good and bad, bad here was just that the molecule would not stay together, it would fall apart. Specifically in the DFT composition. So we did three things. And the third thing, that's something that can frequently happen with these types of complexes about 50% of the time, especially if you have a machine learning model that doesn't know the rules of good and bad molecules, choosing for you what a promising material will be based on properties alone.
Okay, I have another question. So these days I read some papers that, for instance, about the polymer science and maybe molecular dynamic. People are trying to use some nanoparticles for some certain purposes. For instance, they want to enhance the glass transition temperature or some molecular properties. And usually they start several times to repeat that using this different material as nanoparticle to enhance the properties. That was a trial and error process. So is it any way to use machine learning to, before testing that nanoparticle, to find the most optimized, I don't know, nanoparticle for suitable for that polymer or for that material or not?
So the application I didn't show you today is probably closest to what one would want there. So what you're thinking of is something that would benefit from experimental design, or called expected improvement or efficient global optimization. So say one has 3 simulations or experiments that say good, good, bad. Which is the next point that you should go to and carry out an experiment or computation and a little bit of sparse data to gain the most new information or to have the greatest promise of improving on what is known currently. And so that's something my group is engaged in, but the work is in preparation, so I didn't tell you about that today. But that doesn't require that you already have a bunch of results that you train on. Most of what I showed you today involved having at least a few thousand results. And so if you had a few thousand results of different nanoparticle and polymer composites, then you might already be done and you might have already found something. But this can help you guide you to how to parsimoniously go out and carry out the next experiment or simulation without knowing everything yet. So that's probably a useful application of machine learning in such a case, but I'm guessing based on what you have told me, that's not my main area of research.
That's okay. Thank you very much.
More questions? Yes, very nice talk. So for the first part, when you talk about, I guess, virtual screening of cat-based mechanism, I wonder, in that case, I'm guessing it's kind of a clear consistent in terms of, you know, overall data cycle, you know what are the 2 key steps that are challenging, and you're trying to address that issue. Now, I wonder how important is that for your approach to have a well-established regression method? For example, if we do have multiple pathways possible, can you still take a similar approach with the consideration that changing the structure might lead to one mechanism favored over the other? Will that affect your overall result?
That is something that we're trying to think of right now in terms of water oxidation catalysts. So everything you mentioned is what we're trying to worry about. So specifically, if changing the structure changes the mechanism, and the first thing we're trying to do, I'd say more, is trying to understand how that relates to stability, and so inactivation, and if the mechanism of stability, the mechanism of how a catalyst gets inactivated changes when the structure changes. But the question you asked about multiple steps and changing mechanism is also really important. In that case, we were just trying to demonstrate it, so we focused on 2 steps, but for sure even there's questions of the rebound not happening or different types of reactivation. So it was a gross oversimplification. our particular approach, we are trying to accelerate the screening of intermediates, but it's not our focus to go out and specifically discover mechanisms totally unknown, because I think other people have done that well. But we do use a series of templating strategies so that once we've computed one intermediate, we can very efficiently use that structure again to compute other intermediates. And I'd say the main strength of what we do is more that because we're building independent models on each intermediate, which I didn't show. We have that now with machine learning and independent models for each intermediate. We can start to have predictions that don't rely on the scaling limits. Did that answer your question?
Yeah. More questions? I have
Okay.
one threefold question. Yeah, very interesting. Thank you. I'm looking on it as like an uneducated user for black box and trying to formulate which questions can be asked and received, answers can be received. So it looks like everything that is being done in this area focuses on optimization, optimal structures. And for metal catalyst, it was there were single centers, and for molecules, it was typically one molecule, every intact, a single entity. So I'm looking for going. Are there any fundamental difficulties in going beyond these three borders? So from single spin center to multiple, like molecular magnets, where they'll be oriented to ferromagnetic, antiferromagnetic. From optimization to transition state, like, using it, and from connected to disconnected, like several molecules in one.
So the first two I'd say we've thought about and have actually done work on. I was running slow, so I didn't mention why we stuck to mononuclear octahedral transitional complexes, because I could run DFT calculations with a straight face more than I could for multiple metal centers. But we have done it in the context of metal organic frameworks where metal nodes have multiple metal centers, and so we've extended the featurization there. So we've extended it to periodic systems and to multiple metals. But that work it's a draft on my desk. That's no problem. There's no formal limitation there. I haven't, what our representation lacks, and I think I mentioned it to someone this morning, is we don't handle distance information, which the model can learn in the context of a variety of things, but it's going to fail when there's strong interligand hydrogen bonding. Charge-assisted interligand hydrogen bonding can throw off a property quite well, so you can constrain the metal ligand sphere, and if that were in their data set enough, then the model would learn it, even though our representation is slow, but that's something our representation is going to be slow at learning. We haven't thought a lot about many molecules all sitting in a soup, and I think the last thing is we did build a distance-dependent representation back for a specific application we were interested in, which was predicting multi-reference character. And so in that case, we wanted to learn multi-reference character by stretching molecules, and so we did want a representation where the equilibrium and stretch molecules look the same, which is what we would have with our standard. But we basically built in a Coulombic decay. It's certainly it's an area that we haven't focused on so much because we focused on learning equilibrium properties as you identified. So I'd say some of those things are half to 2/3 answered or done, whereas others we haven't touched, I guess. We took the wide space.
Oh, there's one more question.
So you just said that you only learned equilibrium, but I thought during your presentation you said that you used the neural network to optimize like the nearest sphere, and then you let the other program optimize the rest.
That's right.
So how do you do optimization if your model predicts the same features no matter the distance?
So what the model is predicting is what the geometry optimized bond length would be, dependent on spin.
So that's one of your features.
And that's, no, so what the input is the chemical graph, and the output is the bond length should be 2.1 angstroms.
Okay.
So then we feed that into a structure assembly, and it's just a choice that we made several years ago that we wanted to learn that. So for instance, Graph-based learning, the rationale is graph-based learning generalizes better on small data sets. If we required information about distances as inputs to the model, then our model would generalize less well, is sort of the story. But if you think about it, when we call a data point is only the output of a geometry optimized result, so it takes us maybe 100 steps of a geometry optimization to get one data point. Whereas if we've been using all that time, all of that relationship to build a potential energy surface, we probably, on some level, should be doing that as well. Because a distance-dependent representation at this point, now that we have, thousands and thousands of complexes in our full data set, probably could start to learn the full potential energy surface. But it's a simplification we took to move into a space where no one else was doing machine learning. I think as Dimitri identified, we cut some corners because we were trying to get into a space that was challenging to start. Or we certainly, maybe cutting corners is a bad way to say it, but we chose to narrow the scope of the challenge.
Last call for questions? More questions one? More questions two? More questions three? Let's thank Professor Kuhn once again.